particular how many elements are in those. So if we look here, we have 1, 2, 3, 4, 5. Kind of like the width is 5. Well, each of these is called a column. So those are columns. And there are, in fact, 5 columns. We have 1, 2, 3, 4, 5 columns. Going the opposite direction, we have 1, 2, and 3. And these are called rows. I think columns are kind of fitting because think of like a coliseum is filled with a whole bunch of columns. They go up and down. And then we just have rows going across. Well, the number of rows we have are 3 rows. We have 3 individual rows. Now, when I'm building a matrix, we need to know the size of it in order to occupy it. When we give sizes of a matrix, we go row by column. So in this case, we will have a 3 by 5 matrix. A 3 by 5 has 3 rows and 5 columns. So those are the basics of what a matrix is. But we've all seen matrices last year, hopefully in Algebra 2. I know, in fact, she went over it. I've looked at her stuff, so you, in fact, have seen matrices before. All right, but really quick, something easy on the test, and it will show up, is just determining the size of each matrix. The size is just how many rows by how many columns it has. So this one has 1 row and 3 columns. So that is going to be a 1 by 3. The next one has 3 rows, 1, 2, 3 rows, and it has 1 column. Square ones are nice because you can't really get them wrong. You can mix up your rows and columns however you want to. It is a 2 by 2. And finally, this last one has 1, 2, 3 rows, and it has 1, 2 columns. So this is a 3 by 2. But as I said yesterday, we're going to start using matrices to solve linear equations. So before we do that, we have to talk about something called an augmented matrix. An augmented matrix is a way to specifically write a system of equations as a matrix. So this is the representative of these two systems together. Where if we look at A, B, C, D, these are just our coefficients. So this column houses our coefficients. Yeah. And more specifically, the A and B are going to be coefficients for our x variable, and C and D are going to be coefficients of our y. E and F are just going to be constants. In other words, just that number that's over here. But I think the big takeaway is when we convert it to a matrix, we no longer have x and y's in our matrix. I don't put ax, by. In fact, all of these are just going to be numbers. You're going to have to know which column is represented by which variable. All right, it will not be written on it. It will be strictly just numbers. So we're going to do some examples really quick. So this one says, write the argument, or the augmented matrix for each system and vice versa. So I want to write this as a matrix. In order to write it as a matrix, we have to have all our variables on one side and lined up. I want all the x's lined up, all the y's, and all the constants. So the first thing you're going to do before you put it in a matrix is you're going to get all of your variables on the left-hand side, and then we'll put it in an augmented matrix from there. So the first thing I want to do is I want to get that y to the other side. So we're going to do x minus y equals 3. So it's almost like I'm lining it up if I'm doing elimination. so I can see what numbers line up with what. So in the other one, I have to add x to both sides, so I'm going to have x plus y equals 4. Now we're set up to put it into an augmented matrix. As I said, an augmented matrix will no longer have x's and y's in it. You will just have to know which column goes with your x and which column goes with your y. So we're going to have something that sets up like that. And all we're going to do is we're going to take all of the numbers that are in our equation. So if we look in front of the x, there's actually a 1 hanging out there. So in that top left corner, we're just going to put a 1. In front of the y is a -1. And then we have a 3. For our bottom equation, we have 1x, so we'll have a 1. We have 1y, so we'll put a 1 there. And we have a 4 as our constant. We don't usually write this on here, but just recognize that these are all of our coefficients for x, and these are all our coefficients for y. Our next example is when we write our augmented matrix, you have to realize that every single variable needs to be accounted for in every single row. So when we start making this augmented matrix for this one, we're going to notice that we have a 1, a 2, a -1, and a 1. However, down here we're missing a variable. So you have to be able to recognize that we really have 0 y's. All right, normally you wouldn't have to write this. You just recognize we'll put a 0 in that y. But just for the sake of our notes, I'm going to rewrite these as we're going to leave the 2 alone, the x plus 2y minus z equals 1. But I'm going to rewrite the next one as 2x plus 0y plus 3z equals 5. So I remember that there's a 0 there. Then we have 3x minus 2y plus z equals 0. Now we're just going to take all those numbers. Everything's in order. We have all our x's lined up, all of our y's lined up, all of our z's lined up. So it's all set to put into an augmented matrix. So our first equation is 1x, 2y's, -1z, and a 1. Our second equation is 2x's, 0y's, 3z's, and 5 for a constant. And our final one is 3, -2, 1, and 0. And that is our augmented matrix. So the big things are, make sure that you have everything simplified where you have variables on the left side and your constant on the other. And make sure you at least understand that if you're missing a variable, you have to put a 0 in its place. And you don't actually write 2, 3, 2, 3, and 0. The 0 has to go specifically with that variable that's missing. All right, any questions about writing augmented matrices? Okay, then let's go the opposite direction. The opposite direction is I give you an augmented matrix and you have to write it as an equation. As a quick reminder, you have an x column and a y column. Remember, those variables are, we pick them as mathematicians. This could be A and this could be B. But as soon as you pick a variable, it has to go to both of them. As soon as I call the top one B, these all have to be B, but usually we use x's and y's. So our first one is we have 1x, so we'd have x plus 0y's equal 5. The other equation would be 0x plus 1y equals 1, but you'd most likely rewrite that as just x equals 5 and y equals 1. This one right here is the key matrix we're going to use to solve linear equations. And that is because this is our identity matrix. It is the one that ends with x equaling 5 and y equaling 1. So if you ever see this identity, you actually know the values of your variables. And that is going to be our key to actually solving these, but we're going to talk about that down there in a second. All right, our next one. We have an augmented matrix. You're supposed to write it as a system of equations. So we're going to look at that first one. We have 2, 3, 4, and 6. So we'll have 2x plus 3y plus 4z equals 6. Next row, we have negative 1x, or just negative x. We have 0 y's, which can be handled by either leaving it blank, or you can write a 0 y. Plus 5z equals a negative 2. And finally, we have x minus 2y plus 3z equals 1. Once again, you can either put 0y or you can completely omit it and just have negative x plus 5z. I don't really care, as long as you recognize that 0 means you just don't have one more. All right, so that is going the opposite direction. The last thing we have to learn before we actually learn how to solve using matrices is row operations. Row operations work just like when you're dealing with equations. You can multiply both sides of an equation by 2, and it still stays balanced. When we do elimination, we add 2 equations together, and it still stays balanced. All 3 of these are just based upon those principles of equations, because at the heart of this is 2x plus 4y equals 8. This is negative 1x plus 3y equals 2. We're not doing anything that breaks those equations. We're just kind of embedding it into this matrix. All right, so everything we're doing keeps everything balanced. So the first thing I'm allowed to do is I'm allowed to interchange 2 rows of a matrix. What's actually happening here is, say I have these 3 equations, and I erase this one and write it down here. I didn't change anything. I just wrote it down below instead of up on top. So that is the first thing we're allowed to do. However, when we do matrix operations, you have to tell the person or yourself reading it what you did. You can't just change something and hope someone knows exactly what you did. So all the stuff we're going to put under here is exactly what I'm doing. So when I want to interchange my 2 rows, I'm going to write row 1, and then I'm going to use a double arrow, and I'm interchanging it with row 2. You have to write that to do this correctly. So that means I am now allowed to flip those 2 because I said I was going to do it. So we can now do it. So anything that's in our first column is now going to be in our second column. Anything in our second column is going to, or row is going to be in our first row. So the 2 and negative 1 are going to switch places. So I'll have negative 1, 2. The 4 and 3 will switch places. So I have 3 and 4. And the 8 and 2 will switch places. So I'll have 2 and 8. The next thing I'm allowed to do is I'm allowed to multiply 1 row by a non-zero number. Well, that's just like multiplying both sides of an equation by 2 or 3. In fact, let's just go ahead and do that. I'm going to multiply the first row by 2. So we're going to now have 4, 8, and 16. It's still balanced. But once again, I have to tell the reader what I did. So we're going to write it like this. We're going to say multiply row 1 by 2, which is going to look just like that. 2 times row 1. And now what we're going to write is an arrow. That arrow means I'm going to replace something. I'm going to multiply row 1 by 2, and then I'm going to replace the existing row 1 with those new values. So this arrow just means replace. So I'm going to multiply everything by 2, get rid of it, and replace it with those new numbers. So our new matrix is going to look something like this. 2 times 2 is 4. 2 times 4 is 8. 2 times 8 is 16. And I didn't do anything to row 2. Note, I didn't write anything about row 2 in here, so row 2 will remain the same. I do want to reiterate, you will lose points if you don't write what you're doing. Brody?
What was the point of flipping it in the first step then?
We're just allowed to. Each of these are going to start with the exact same matrix. Okay, I'm not moving on. I'm just showing, hey, I can multiply row 1 by 2. Well, if I have that same equation, I'm also allowed to adjust this. If I have the same equation, I'm allowed to do this.
Oh,
I'm not showing any steps. They're just things you are allowed to do.
Okay.
And you're going to use it later on. These are all skills that we're going to need later on. So each one starts with a fresh. Maybe I should have picked different numbers. All right, the very last thing we're allowed to do is we are allowed to multiply a row by a number, which we already did. And you are then allowed to add it to another row. So it's going to look something like this. I'm going to write it first, and then we're going to actually do it. So I'm going to say 2 times row 2. I'm going to add it to row 1. And as soon as I add it to row 1, that means it has to be replaced for row 1. It means I'm taking this, multiplying it by some number, adding it here, and then replacing this row with those new values. It can seem very confusing out of context. It'll make more sense when we're actually doing it in practice. So what we're going to do is we're going to multiply every element in row 2. And then we're going to add it to that corresponding element here. So we're going to take 2 times that -1 that's in row 2, which will give me -2. And then we're going to add it to row 1. And perchance, we don't normally do this, but just for the sake of this, 2 times row 2 would just be -2, 6, and 4. So those are really the values we're adding to row 1. So once again, 2 times -2 is -2. Add that to the row 1 element. -2 plus 2 is 0. So our top left would become 0. Now we're going to go back here and say 2 times 3 is 6. That 6 plus that row 1 element would be 10, because it'd be 6 plus 4 would give me 10. And finally, we'll do 2 times that 2 here, which would give me 4, plus that 8 is going to give me 12. My arrow says the only thing I'm replacing is row 1, which means row 2 is not actually changing. Row 2 is just going to remain -1, 3, and 2. And like I said, all these will make more sense when we're actually using them. Yes?
So when you're doing like something like that, do you just follow the order like from left to right?
Mm-hmm.
So there's no like you have to do like the switching first?
Yeah, you can do whatever you want, whatever makes... we're going to apply this to a bigger way to solve things. So sometimes it makes sense to switch something,
Okay.
and sometimes it makes sense to multiply something by just one number. Sometimes it makes sense to multiply and then add. It's going to be this nifty little pattern that once you get accustomed to it, you're going to know exactly what you need to do at any given situation. All right, it's not going to be like, you don't have to go through a checklist. You don't have to go, okay, what do I need to do this matrix? You will know. You will know looking at it what you need to do once we get into it. We just have to first know we can do it, and then you'll see kind of the pattern when we do the first thing. All right. I think I'm missing the slide, so I got to put that in real quick. Gauss-Jordan elimination. You are right here. Cool. Gauss-Jordan elimination method. 100% based upon that identity matrix we just talked about before. Gauss-Jordan elimination is based solely on this fact. In fact, the whole goal of Gauss-Jordan elimination is to use those methods we just came above to write an identity matrix. And that identity matrix is this 1, 1, 0, 0, where top left to bottom right are going to be 1s. So this is, in fact, the identity matrix we're going to be looking for in every one of these problems. And off to the side, I'm going to do another example. Let's say we had x, y, and z. The identity matrix on something like that would look like this, where we'd have 1s going down. Since it's augmented, we should have A, B, C. So we have 1s going from top left to bottom right. Everything else will be 0s. If I had a 4 by 4, we would have one more 1 down here, and everything else will be zeros. You have to know what this looks like, because your goal is to change a matrix to look exactly like this. But if you don't know where you're going, you're not going to know how to get there. So you have to know what the identity matrix looks like. It is 1s in the top left, runs 1s all the way down, everything else is zeros. All right, that is our identity matrix. Can't stress how important it is. You have to know what that looks like. And that is because we are about to use it. We are supposed to use Gauss-Jordan elimination to solve this system of equation. Yesterday we talked about graphing, elimination, substitution. Today we're going to talk about using Gauss-Jordan elimination method. It's going to seem like a lot of work. It's going to seem very, very confusing, but it is helpful with bigger matrices, especially because you can do this in your calculator in 2 days. So in order to use Gauss-Jordan elimination, the first step says work left to right. Realistically, your first thing you have to do is first write it as a matrix. Gauss-Jordan elimination method requires matrices. So the first thing we're going to do is we are going to write it as a matrix. So our matrix is going to look something like this, where we have 2, -4, 16, 3, 1, and 3. All right, now we'll go to the steps. The steps say work left to right. So I'm going to complete this column, and you know what I mean by complete in just a second. We're going to complete this column before I even care about doing anything over here. So we're going to work left to right. We're going to get this completed first, and then we're going to do this. Our whole goal is that this is a 1, this is a 1, this is a 0, this is a 0. Surprisingly enough, this 1 isn't going to help me because it's going to change in just a second. All right, so your goal is to get an identity matrix. Now this says locate which value needs to be 1 first. So in my mind, I'm like, okay, identity matrix, I'm looking at this column first. Which of these needs to be a 1? It's this one. I need to turn this one into a 1, so I'm going to start with that. So we're going to look at our 2, and I generally circle it because I know which one needs to be changed then. That needs to be a 1. Now, sometimes this can be as easy as switching your 2 equations. Let's say this was a 1 down here. Let's say this was 1, 1, 3. I could just switch these 2 and I put a 1 there, and I'd be done. In this case, I can't just switch them, so I need to use another method to change that 2 into a 1. Well, changing a number into 1 isn't hard. You just multiply by its reciprocal. 2 times 1/2 equals 1. So all I'm going to do is I'm just going to half this entire row. You can't do something in one element. You have to do it to both sides. So we're just going to multiply row 1 by 1/2. So it looks something like this. Take 1/2 of row 1 and replace row 1 with those new values. You do have to say which row you're replacing it with. Then we're going to put a little arrow off to the side saying the next matrix you see will be the one I just altered. 1/2 times 2 is 1. Boom. I got 1/4 of my identity matrix done. -4 times 1/2 is -2. 16 times 1/2 is going to be 8. I did nothing to row 2, so you're going to write row 2 as it was to begin with. A 3, 1, and 3. Work left to right, working on it. I located the value needed to be 1. I used multiplications to make it a 1. Step 3 is to locate which one needs to be 0. So we're going to make all the other elements in that column 0. In this case, we only have to make 3 0. So I'm going to circle 3. And that one needs to be 0. Here's where the pattern comes in. You can't really use multiplication to make something 0, because you're not allowed to multiply both sides by 0. Otherwise, you make the whole thing 0. So what you're going to use, and what I kind of think about is, I forget about the rest of this. I forget about kind of this rest of this information. I'll bring it back in just a second. I'm allowed to multiply this 1 by any number I want to, and I'm allowed to add it to this 3. Well, if I multiply this 1 by negative 3 and add it to 3, I end up with 0. Negative 3 plus 3 equals 0. So let me bring everything back in. So that means what I want to do is I want to multiply the entire row 1 by negative 3. I then want to take that value and add it to row 2. And I want to replace that information with row 2, because anything I have circled is going to be a row I want to replace. Yes?
Are we allowed to state like both of those changes in one step or no?
I don't highly suggest it.
Because it gets confusing because there's already a change and then
Yes,
based
and
on the change you're making another.
you have to look in the future and then figure out what you're multiplying. You lead to you're going to make tons of mistakes on this to begin with. Let's just do one step at a time.
All right.
If you get really good at it, then you can start doing a whole bunch of stuff at once. But I'd practice, crawl first before you start running.
Okay.
Typically speaking, even like me as a math teacher, if I was doing something like some kind of proof, I would show these each individual steps. All right, so right now I am multiplying everything in row 1 by negative 3. And then we're going to add that result to our second, and whatever that result is, we're going to replace it with. So we're going to move on to our next matrix. First of all, nothing's happening in row 1, so I'm going to leave that alone. Because the only thing getting replaced is the stuff that I've circled. We're going to do negative 3 times 1 gives me negative 3, plus that 3 equals 0. I'm going to say right now, you really have to pay attention to what I'm doing. This can be really confusing at first, but the better you do in class, and the more you do in homework, the easier it becomes. Negative 3 times that element in row 1, negative 3 times negative 2 is a positive 6, plus row 2 would be a positive 7. Now I'll do negative 3 times 8, which will be negative 24, plus 3 would be a negative 21. Now you can see our identity matrix starting to show up. I have a 1 and a 0. That means this column is done. If you have a 1 in the top left, everything else is zeros, you are done in that column, which means you move on to the next column and you go back up to your step 2, which says locate which one needs to be 1. You always find your 1 first. The one that needs to be 1 is this 7 here. Creating the 1 is usually the easiest part. Multiply by its reciprocal. So to turn 7 into 1, I'm going to multiply all of row 1 by 1 over 7. Or row 2, I'm sorry, we're in row 2. And that is going to replace my row 2. So I'm multiplying all of row 2 by 1 over 7. And I'm going to go ahead and copy this and put it on a new slide so I have room for it. Maybe I am. There we go. All right, so I'm going to come down here and show the result of that. So I'm going to leave row 1 alone, 1, negative 2, 8, because I didn't do anything to it. Row 2, I'm multiplying by 1 over 7. 0 times 1 over 7 is still 0. 7 times 1 over 7 is 1. Negative 21 times 1 over 7 is negative 3. Almost done. You always find your 1 first, and then you make everything else 0. So I need to make that 2 a 0. But realistically, I'm just asking myself, I need to multiply by this 1 by something, so when I add it to this negative 2, it turns to 0. If I multiply 1 by 2, 2 plus negative 2 is 0. So that means I'm going to multiply this entire row by 2, add it to this row, and replace that row with that information. So underneath, it's going to look like this. Take row 2, multiply it by 2, add it to row 1, and replace row 1 with that information. Move on to our next matrix. 2 times 0 is 0. 0 plus 1 is still 1. If that ever changes, you made a mistake. All right, your 1s and 0s should always remain. If you made something a 1 and you made something a 0, it should never change, otherwise you made a mistake. Now we'll have 2 times 1 is 2. 2 minus 2 is 0. That's what we needed to happen. 2 times negative 3 is negative 6. Negative 6 plus 8 is 2. And underneath, we were already done with 0, 1, negative 3. Now we have our identity matrix. The long way to write this would be, 1x plus 0y equals 2. This would be 0x plus 1y equals negative 3. What you should really do is as soon as you have that 1, 0, 0, 1, is you should just write it as x equals 2 and y equals negative 3. You can also write the point to negative 3. I'm not concerned with how you write the answer, as long as you get to that 2 and negative 3. All right, you're going to make mistakes. It's a lot of stuff going on. You're kind of keeping track of a lot of information in your head. That's why I strongly suggest you just do one step at a time. Otherwise, you're trying to keep too much in your head. All right, there's 2 of these on the homework. The rest of the homework should be pretty easy because most of it is just what is the size of this matrix. Rewrite it as an augmented matrix. The last 2 are going to be your hard ones. Work on them. The harder you work on this stuff, the easier it's going to be because you know for a fact these problems are going to be on the test. And if you don't know what's going on, it's going to be super hard. Tomorrow we're going to use a bigger one. We're going to do a 3 by 3, which means we're going to have a whole nother row in here. So it's going to be a lot more involved. And the more you work on it tonight and understand what's happening, the easier tomorrow is going to be for you. All right. The rest of the time will be for you. Actually, before I move on, did anyone have any questions on the homework? I think most of us almost had it done before we left. All right, if there's no questions for me, the rest of the time is yours. Please have your homework out. I'm going to walk around and I'm going to check.